Okay, so single qubit states, right? We will typically denote the two possible classical states that a qubit can be in as 0 or 1, where this this sort of funky looking notation is called the Dirac notation, and we refer to, so the way we pronounce this is ket 0 and ket 1. Okay, and so the general state of a qubit is represented as, you can call it psi, and it's some linear combination, alpha 0 plus beta 1, where alpha and beta are complex numbers. Okay. As usual, you should ask questions in the chat, or you can also speak up. So the state of a qubit is specified by these two complex numbers, alpha and beta. And now, sort of mathematically, the state of a qubit, since it's specified by these two complex numbers, alpha and beta, it can be represented as a two-dimensional vector with complex entries. And we represent it as you can see here. Okay, so formally, the state of a qubit is nothing but just a two-dimensional vector with complex entries, alpha and beta. Yes, complex entries, not real, right? So the question that I have for you, right? So this is, let me answer another question. Are qubits the empty glass, filled glass analogy? Yeah, so if you, to some extent, so if you consider empty glass to be 0 and filled glass to be 1, a qubit is kind of anything in between. But the very crucial part is that if you were to sort of represent something that sort of goes between empty glass and filled glass, all that you need is, a single positive or non-negative real number, non-negative, right? That goes from 0 to 1, where 0 would be your sort of empty and 1 would be your full. But you wouldn't need negative numbers or complex numbers to represent, a state that is in between empty and full. Crucially here, we are using two complex numbers. So not only they can be negative, but they can also be complex. So this is how we define a qubit. It's just a two-dimensional vector. Let me actually remove this. So let me ask you before, okay, let me ask you then. So with this definition of a qubit, okay, and looking back to what I told you here, that, the general state of a qubit is, we can represent it as a linear combination of this 0 state and this 1 state, okay? Then the question that I ask you is, what vectors, if we were to write them in this vector notation, just like we wrote psi here, what vectors would the states ket 0 and ket 1 correspond to? I would like you to help me answer this question. So Jacob says 1, 0, and 0, 1. Any other thoughts? Yes, exactly. That is correct. So 0 and 1 correspond to the standard basis vectors, right? So, I can write 0 as a linear combination, of course, of 0 and 1, where alpha is equal to 1, right? And beta is equal to 0, right? And I can write 1 as a linear combination of 0 and 1, where alpha is 0 and beta is 1. Okay. And so with this formalism, we have that 0 and 1 are the standard basis vectors. So any qubit state can be written as a linear combination of the two standard basis states, as we have here at the bottom. So now we'll refer to the coefficients alpha and beta, from here on in the camp as amplitudes. That's how we call them. And they can be interpreted sort of, if you think of the analogy of the wave function that we had before, which was sort of a function over sort of a continuum of locations, right? But if you think of that analogy, then the coefficients alpha and beta can be thought of as the height of the wave function at a particular location 0 and a particular location 1. Okay, they're sort of psi of 0 and psi of 1, if that analogy is helpful. So in any case, this is the general state of a qubit. Alpha 0 plus beta 1. Okay, so now what about measuring single qubit states? Okay, so the process of observing whether the qubit is actually in the 0 state or the 1 state is referred to as a measurement. Now, don't worry about the physical part of what happens to a measurement. Here we're in this module, we'll only be worried about the math. So we'll sort of abstract out all of the physical components of what a measurement is and what it's not. We'll just worry about, you know, postulates and the mathematical formalism. So when you perform a measurement, you obtain an outcome, either 0 or 1. And after the measurement, the state of the qubit, this is the rule. The rule says that after the measurement, the state of the qubit collapses to ket 0 if we got the outcome 0. And it collapses to 1 if we got the outcome 1. And what about, you know, the probabilities of this collapse? Well, so if we are measuring the state psi, which is alpha 0 plus beta 1, and again, you know, just to clarify, I'm using two different notations, right? There's the vector notation to represent psi, right, the qubit state, or I can also write it in this way using the ket notation. We'll typically use the ket notation, but, you know, those can be, the two notations can be used interchangeably. So now if we measure this state here, Born's rule says that we'll obtain outcome 0 with probability the modulus of alpha squared, the magnitude of alpha squared, and we'll obtain outcome 1 with probability the modulus of beta squared. So Shriyans is asking, so the kets are like polarizers. Well, the kets are like the two, if I'm understanding your question, if you're thinking of a Polaroid filter, you know, the ket 0 might be, you know, a vertically aligned sort of photon, and ket 1 might be a horizontally aligned photon. Okay. So now we all know that the probabilities of all the outcomes, in this case, there are only 2, 0 or 1, they must add up to 1. So what Born's rule implies is that these two quantities, the modulus of alpha squared and the modulus of beta squared, have to sum to 1. Okay, so this is the only additional condition that we add to a state of a qubit, alpha 0 plus beta 1, with a constraint that modulus of alpha squared plus modulus of beta squared is equal to 1. Does this make sense so far? I just want to pause because, you know, this is, it's very important, obviously, that you understand what qubits are. It's essential to going forward. So let me, you know, if you're all happy with what we've said so far, you can say it in the chat. If there's any question, you can ask it. So Miles, when does the qubit collapse to 1, 0? It only collapses to 1 or 0 if you decide to make a measurement. Okay. Now we will not worry about what does it mean to physically make a measurement. Okay, but you know, the formalism of quantum mechanics says that there is the option of making a measurement, and when you do that, that's when you either collapse to 0 or 1. Now, if you really care about the physical intuition, then you know, a measurement going back to sort of the double slit experiment would be when you hit the detector screen. The detector screen says whether you go, well, or a better example is whether you pass sort of through the left slit or to the right slit, right? There are only two slits. You can think of this as being 0 and 1. That's when you're making a measurement. How does it choose what value to collapse to? Well, the value that it collapses to, it's determined by this probability here. which is given by Born's rule. Okay, so I mean, we can go into a philosophical discussion of like, when is it actually decided, like whether the photon will collapse to 0 or to 1? Or you could even ask me, for example, you know, did the photon know all along that it was going to collapse to 0? You know, even though I haven't made the measurement yet, did the photon know all along that it was going to collapse, say, to 0? Well, the answer to the question turns out to be no, that the photon only decides at the very moment, the photon or the qubit decides only at the very moment when you measure it, whether it's going to collapse to 0 or 1. But for the purpose of the mathematical formalism, all that you have to know is that when you measure, there's a probability distribution, and the weights of this distribution are precisely, you know, modulus of alpha squared and beta squared. To answer Miles, yes, it would be completely uniformly random if alpha and beta were 1 over square root 2 exactly. Is there a derivation that getting outcome 0, 1 has a probability of alpha beta squared? That's a great question. And the answer to this is no, not really. It's not something that you derive. It's an axiom. It's an axiom of quantum mechanics. This doesn't mean, you know, that, you know, it's something that you know, sort of have to be unhappy with, or that we can't grasp. So it's an axiom, which means that from this we derive sort of rigorously our predictions of what's going to happen in an actual physical system, and we check whether these predictions match the outcomes of the experiments. And if they do, then we can get more confident that this axiom was indeed correct. But it's not, crucially, it's not something that you derive. What is the physical meaning of 0 and 1 in the cats? So the physical meaning could be, for example, that, you know, 0, to give you a concrete example, but this is obviously not the only physical example. You can make a qubit out of, you know, physically, you can make a qubit out of, you know, a gazillion sort of physical systems. But one example is you can have a photon that, I mean, I don't know if you know, but I'll tell you now that the photon is usually polarized. So it can it can have a polarization that is kind of, you know, spanning a unit circle if you want. And in particular, you know, cat 0 could be corresponding to the photon being polarized vertically, meaning that sort of that the wave that describes the photon oscillates in a vertical direction, and 1 corresponds to the photon oscillating horizontally. What does cat mean? What does cat mean? So it means, you know, there is also another symbol that I haven't introduced. I don't think we'll introduce in this course, which is called bra. And it's basically the cat the other way around. So it kind of looks like this. And so basically the reason why it's called cat is because when you put them together, it's kind of a bracket. Okay, it's just what people came up with. Nothing deep about it. Does the system measure at a certain point, or do we enforce a certain measurement? So it can be both. Okay, so ideally, when we're doing computation, the whole point is we want to be able to control exactly what evolution our quantum state is undergoing, and exactly when we're making the measurement. This is the whole point of trying to build a quantum computer, is we want to be able to, at any given point, decide what evolution I want to sort of put my quantum state through, and when exactly to make a measurement. Unfortunately, though, it happens in practice that it's often this sort of the environment, the surrounding sort of environment, that accidentally, if you will, measures our precious quantum state, because, you know, be it, you know, there are many particles in the air, there's temperature. So unfortunately, quantum states are very fragile, and one of the main problems in trying to control quantum states and making them do what you want, like in a quantum computer, is that you have to keep them at very low temperatures, because otherwise the surrounding environment would accidentally measure your state and collapse it, which is not necessarily what you want. But for the purpose of quantum computing, right? Whenever we're talking about quantum computing, we're assuming that we have control over these operations. So we get to decide when we make a measurement, when we do a certain evolution. That's assuming we have a quantum computer. So what properties do alpha and beta represent? So alpha and beta would be, if you want, psi 0 and psi 1. You can think of, in the previous class, we had this psi of x, where x was, a continuum of locations on the detector screen. Now imagine that there are only two possible locations. Or for instance, you can pass through the first slit or the second slit. Okay. And your wave function is just specified by, the value at these two possible locations, psi 0 and psi 1. So this is how the analogy with what we had before, if it helps you. Okay, yeah, it's great that you all are asking many questions. I hope you're starting to get it. This is very important. Okay, let me proceed. So let's do an exercise. I'll put it for you. I mean, we have a bunch of exercises that you'll do later in exercise session, but then let's do a few together. So, we're given a state psi, alpha 0 plus beta 1, a qubit state. Suppose that alpha is 0.68 and beta is 0.4 plus IB. I is the imaginary unit, B is some real number. And what I ask you is to determine what is the value of B. I'll give you a minute to, let's see if you can answer. So Shriyan says 0.35. I believe that is not the correct answer from what I recall. So let's see, Loren is saying beta is equal to 1 minus alpha squared. So 1 minus, well, no, but alpha here you're writing, alpha squared, okay. No, but that's not quite correct, right? Loren, the problem is that it's not beta that is 1 minus alpha squared. It's the modulus of beta squared that is 1 minus the modulus of alpha squared. So I see some very nice answers. So the correct answer is, I believe, 0.61. So I think Anjali and Jagrit got the right answer. So if you did not get the right answer, don't despair. I mean, I didn't give you very much time. So later, make sure can I walk through it? Okay, I can walk through it. Yes, absolutely. That's a good idea. So I don't know if I want to do the actual calculation. Let me just walk through it in words, okay? So we want to use this modulus of alpha squared plus modulus of beta squared equals to 1, okay? So, let's expand out the modulus of beta squared, right? We know that beta is 0.4 plus IB, right? So what is the modulus of beta squared? It's, if you remember, it's the real part squared plus the imaginary part squared. So let me calculate it. It would be 0.4 squared plus beta squared. Okay, what's 0.4 squared? 0.16. Okay, so 0.16, oops. 0.16 plus b squared. Okay, so if we expand out this modulus of beta squared, we get 0.16 plus b squared. Okay, so now we can bring the 0.16 to the other side. We can calculate also the modulus of alpha squared, which is 0.68 squared, which is 0.46. Okay, so basically what we get, I'm doing it in my head, but so we get beta squared is equal to 1. Sorry, not beta squared, I keep saying beta, it's b squared is equal to 1 minus 0.16 minus 0.46. Okay, so now 0.46 plus 0.16 is 0.62. Okay, 1 minus 0.62 is 0.38, and this is b squared. Okay, so b, so this is b is the square root of 0.38, and hopefully we get 0.61. Fantastic. So unfortunately, I should have had a Jamboard so I could show you the calculation by hand. I promise I'll do it later when we do the problem session. I'll have a Jamboard and I show you if you're still having trouble, okay? For now, let me proceed. Okay, here's another example. It's a simpler example. We can do it together. So consider a qubit in the state psi, the square root of 2 over 3, 0, plus 1 over square root of 3, 1. Okay, now suppose we make a measurement and we obtain outcome 1. Okay, now immediately after this measurement, suppose that we measure the system a second time. What would the result of this second measurement be? Lorentz is same. So we measured the first time, we got outcome 1, and now we measure it again right away. Okay, yes, so the correct answer is that we get the same outcome, okay? So the people who said that it's the third option, that's incorrect. Right, so the reason why we get the same outcome is, you know, remember what is the rule when we measure, right? If we get outcome 1, the state collapses to ket 1. Okay, so now the new state is ket 1. If we measure again a second time, we apply Born's rule again, but now the state is ket 1. And so we will obtain outcome 1 with probability 1. Right, that makes sense? Exactly. Jason says this correctly. This is exactly the collapse. Why not the last? No, it's the qubit is still, I mean, it's still a quantum. Well, so you have a good point. So it becomes classical, but one important point to make is that any classical system, right, even just exactly 0 or exactly 1, it's always a special case of a quantum system, right? Ket 1 is the special case where alpha is equal to 0 and beta is equal to 1. So any classical, we call them classical, right? If they're exactly 0, exactly 1, but they're also still a special case of a qubit state, just that alpha is equal to 0 and beta is equal to 1. How do you uncollapse a bit? Well, it's a good question. You can't uncollapse a bit. You can't reverse. So crucially, the measurement operation is not something that you can reverse. Once you measure, you actually lose a lot of the information you had before. The probability, no, the probability actually, so the probability affects both measurements, right? So in the first time that we measure, the state is square root of 2 over 3, 0, plus 1 over square root of 3, 1, okay? Now we make the first measurement, we apply Born's rule, right? And this, you know, tells us that with probability 2/3, we'll obtain 0. With probability 1/3, we get 1. But now I'm saying, suppose that the outcome of the first measurement was 1. Okay, so we know that the outcome is 1. Okay, which means, according to sort of the rule of what happens when you measure, it means that the state has collapsed to ket 1. Okay, so now you make the second measurement, you again apply Born's rule, except that the coefficients alpha and beta are now changed. So you're still applying the same rule, but now with different coefficients. Qubits are one-time uses. Well, you don't have to create a new qubit. So the state after the measurement will be, in this case, in this example, will be cat1, right? You can still apply quantum gates to it and make it evolve to an actual superposition. So it's not to be thrown away. You can still use it. Yeah, exactly. Miles, you can do a Hadamard, yeah, for example. We'll see that in a moment, or in part 2. Okay, so let me proceed, write the solution when we, yeah, as I said, I don't have to repeat that. Very good. Okay, so now these exercises I will leave for you to do later. Okay, now let's make some observations, right? One thing you might have observed is that the following states, they all give rise to the same probabilities. Alpha 0 plus beta 1, alpha 0 minus beta 1, alpha 0 plus I beta 1. First of all, do you agree that if we were to measure these 3 states, we would get the same probability distribution of 0 and 1? You can tell me if you agree in the chat. Very good. Okay, awesome. So then if yeah, exactly, because you take the modulus squared, right? So the I doesn't matter, the -1 factor doesn't matter. Okay, so then my question to you is, why does it matter that we allow alpha and beta to be complex numbers, or even negative numbers? Forget complex, just negative numbers, because anyways we're taking squares. Why does it matter that why are we even allowing that? Yeah, that's absolutely correct. So the point is that, if you were to measure immediately, then of course you'd get the same probability distribution. But the point is, if you don't measure immediately, right? If you don't measure, oh no, I don't want to go there. But okay, I'm just going to say it in words. If you don't measure it immediately, then actually they could, in the future, end up giving you different probability distributions. For example, if you think of the double slit experiment, you could have an alpha plus 1 interfering with sort of an alpha, sorry, a 0 plus 1 interfering with a 0 minus 1 in such a way that the plus 1 and the minus 1 would cancel out, kind of interfere destructively, and the 0 amplitudes interfere constructively. So if you actually apply quantum evolutions to these 3 different states and measure at some point in the future, you might actually get different probability distributions. It's only if you measure right now that they give you the same distributions. So the real crucial part here, some people mention complex numbers, Fauzan. So yes, they can represent more info, but really the crucial part in quantum computing and quantum mechanics is the negative sign. The complex numbers don't matter too much, but the negative sign are really important because they allow for constructive and destructive interference. And Shriyans is asking, how would they change later? Is it because of time? Yeah, so if you leave them on their own, they could evolve according to Schrödinger's equation. But the point when we're doing quantum computing is we want to build a quantum computer which allows us to control the states in whichever way we want. So if we were to build an ideal quantum computer, we would be able to conserve the state, say alpha 0 plus beta 1. And then at any point that we desire, we can apply a certain quantum gate, and we will see what quantum gates are in part 2. Okay, so hang on for that. But at any point, if we have a quantum computer, at any point in time that we desire, we apply a quantum gate, and this transforms the state of the qubit to some other state. Then we can apply another gate, and do a whole computation as we please, and then eventually measure. And now I claim that most computations on these 3 states, most non-trivial computations, will actually lead to different probability distributions in the eventual measurements that you do at the end. Okay, so let me briefly touch upon the concept of relative phase. Okay, so which is what I was getting to, right? Suppose we have the state psi, alpha 0 plus gamma beta 1. So there's an extra multiplication by gamma, which is some other complex number. And suppose that gamma has the modulus squared is equal to 1, complex number with the magnitude 1. So possible values of gamma would include 1, minus 1, I, for example. But in general, right, gamma could be any a plus ib, where a and b are real numbers, and a squared plus b squared is equal to 1, right? Now, notice that, of course, as we've seen even from the example before, gamma, this multiplication by gamma does not actually affect the measurement probabilities, right? If we take the modulus squared of gamma beta, this is, you can verify for yourself, it should be pretty straightforward. This is the same as the modulus squared of gamma times the modulus squared of beta. And because, we've supposed that gamma has magnitude 1, this is same as the modulus of beta squared. Is gamma squared always 1? No, no, it's not. But here, I'm taking it to be 1 because remember, the state of the qubit has to satisfy Born's rule. So that the modulus squared of the two amplitudes have to add up to 1. So I'm saying, if you start with a state that is valid with alpha and beta, and then you multiply beta by a gamma, which has magnitude 1, you will still have a valid state. That's what I'm saying. Start from a valid state alpha beta, now multiply beta by some gamma, which has magnitude 1, and you'll still have a valid state. Does I also represent the sinusoidal nature in any way? The I in the complex number? No, not really. Well, yeah, not really in a, no, not in a direct way that I can say, yeah. Okay, so this gamma, right? This gamma that we're multiplying. So let's say we start with an alpha beta, right? And we multiply by the beta coefficient by gamma. What we are introducing is what we call a relative phase in this state. Okay, gamma specifies a relative phase in this state. And as we were discussing earlier, what is the significance of this relative phase? Right, measurements, if you were to measure, this would be a very lossy process because you turn some quantum information into some classical answer, or like a basis state, cat 0 or cat 1. So upon measurement, relative phase does not matter. So this gamma can be anything, doesn't matter. But if we don't measure yet, then the relative phase matters a lot, because as I was saying, we can let the state evolve first any way we like. And then only after some sequence of quantum gates we measure, and we would probably get very different probability distributions. So the double state is an example of this, right? As Loren was suggesting, if there were no sort of relative phase, there wouldn't be sort of this interference effect. Right, if you particularly if you're thinking of having the state psi1 here, which is 0 plus 1 over square root of 2, interfere with 0 minus 1 over square root of 2, whatever that means, without thinking too much about it. If you sum them up, you can see that the ones would cancel out, the zeros wouldn't. Okay, without thinking too much about what it means to add them up. Okay, so then another sort of term that I want to sort of introduce is global phase. We sometimes refer to it. It happens that sometimes you find a state in a superposition and it has some overall factor in front of it. And this factor is called the global phase. Like a relative phase, it also has no impact on the distribution of measurement outcomes if you were to measure right there and then. So for example, you can consider the state psi, which is 1 over square root of 2, 0 minus 1. And by measuring the state would result in getting outcome 0 with probability 1/2 and 1 with probability 1/2. And now consider the state minus psi. Okay, you can convince yourself that minus psi is also a valid qubit state, meaning, you know, it still satisfies the constraint that the modulo squared of the amplitudes sum to 1. But now this state differs by what we call a global phase of -1. There's a factor of -1 in front of psi. So both of the amplitudes, the original amplitudes, are multiplied by -1, as you can see here. And the probability of the distribution of the outcomes is the same. Do you agree? Well, yes, right? Because you know, when we take the modulo square of the first coefficient, the -1 doesn't matter, both for the first coefficient and for the second. Okay, but yeah, so actually, yeah, I'm gonna quickly ask you to tell me in the chat, you know, example of valid global phases that are not -1. If you can give me some quick examples. Yes, I. Yes, everybody likes I. Yep. And so now the only thing that I want to point out, and I think this is the last thing that I'll mention in this lecture. So the important difference between relative and global phases. Okay. So as we mentioned, relative phases can be detected if we don't measure immediately and we evolve first. But global phases actually can never be detected. Multiplying a qubit state by an overall factor, like an overall factor that has magnitude 1, actually is completely undetectable. And this will not be clear to you now, but once we define quantum gates, which quantum gates are specify the way in which qubit states are allowed to evolve. Once we get to quantum gates, it will become clear that there's never any chance of detecting a global phase. So watch out that these two types of phases are different. That's it. Cool. That's all I had. We can take a few questions for a couple of minutes, and then I'll let you go on a break. In a relative phase, can gamma be a coefficient in the alpha term? Yes, absolutely. Yeah, absolutely. Yeah. In fact, notice that, when I add gamma, I guess to tie things back to the global phase, I could multiply beta by gamma, right? If I don't care about global phases, I can always sort of pull out a factor of gamma -1. Well, actually a factor of gamma. So then alpha would be multiplied by gamma -1, like gamma sort of inverse, and beta wouldn't be, if that makes any sense. What happens when a qubit doesn't follow Born's rule? No, a qubit always follows Born's rule. That's the axiom of quantum mechanics. So they either evolve via quantum gates, which is what we'll see. There are two types of evolution. Either they evolve by quantum gates, which is what we see in the second part of this module, or by a measurement, in which case they obey Born's rule. The relative phase occurs only if we allow the system to evolve. Yeah, I mean, if you start from, say, let's say, typically when we think of, doing a computation with qubits, you'll initialize your qubit in the 0 state or the 1 state, and then you let it evolve, and then relative phases will appear. Yeah, superpositions will appear, and then relative phases as well. Yes.